Hey everybody, good to see you all again. So, I'm sure you already know intuitively what a sphere is. You can think of a sphere as basically the same definition as that of a circle, except that we just add the caveat now in 3 dimensions. The idea for a sphere is that in a sphere, every point on the sphere is the same distance away from some central point. So it's, in essence, it's a 3-dimensional circle here. Now, some of you may already know what the volume and the surface area of the sphere is, but they may not have explained it to you. So I'm spending this here. So this is going to be an explanation of the volume of a sphere. It's a derivation of the volume of a sphere. Now note that normally when you do this, you're going to need calculus. But here, this is a very clever non-calculus way attributed to one Archimedes. Some of you may know about Archimedes, probably one of the foremost mathematicians and scientists in the ancient Greeks. He's given his name to a lot of things here, but this is probably one of his proudest mathematical achievements, and he thought of it this way. So, he considered an experiment like this. Imagine we have 3 solids on a table here. This over here is a right circular cone with a height of r and a radius of r. This is, we're going to look at half a sphere. So you put a hemisphere on the table. Then he created a cylinder and also did the same thing, radius r, height r. So with that, he's going to try to determine what's going on. So what's going to happen here is you're going to take a plane like this, and we're going to cut it parallel to the base of the table here. So it's going to look something like this here. So our plane is going to slice through the solids like this here. And let's say that this height is some arbitrary height h off the surface of the table here. You'll note that when you do this here, you're going to basically create 3 circles here. There's going to be one circle in green here, another circle in green here, and a third circle in green here. So what we're going to do now is we're going to look at each of these circles here and compute their areas. Now for the cylinder, the circle is the easiest thing here, because the thing is the circle, for a cylinder, the cylinder is consistently the same shape all the way up, consistently the same size. So it's pretty clear that each of these is a circle of radius r, so the area of the circle, so we're looking at the cross sections here. So for the sphere, for the cylinder, it's pretty easy to see that it's just going to be pi r squared, because it's a circle of radius r here, right? Now, in this situation, we look at the cone, it's going to be a little bit different here. The cone's going to be slightly different, but we note that since this is this over here, the radius is r and the height is r here, it makes sense that this here is going to be a 45, 45, 90 triangle. This is an isosceles right triangle, even though I didn't draw it that way. This means that the radius of this here, that means the legs of these triangles are congruent, so that means this leg here should match this over here, and that's the height. So that means this here has a radius of h. So therefore the radius of this is pi h, so therefore the area of this is pi h squared, okay? Now for the circle here, for the sphere, this one's a little bit different, but we can still do the same thing here. We're going to create a center, and we're going to try to do this here. So note that something like this, the radius here is r, and we know that this is h units of up. So we don't know what this is here. Now, this is a right triangle. You can see hypotenuse r, leg length h here. So you can use the Pythagorean Theorem, and we find that that is going to be the square root of r squared minus h squared, right? So that means in this situation here, since the area of this, since this is the radius, this here is the radius of our circle, it's going to be equal to, the area of the circle is going to be pi times this squared. So the area of this circle is going to be pi times r squared minus h squared. So now I'd like you to take a look at these 3 quantities here. We have this, this, and this. So if you look at this for a bit, you should notice something very interesting here. In particular, you can note that it looks like here that you can take these 2 quantities here and subtract them and generate this quantity, right? Pi r squared minus pi h squared, you can think of that as just pi times r squared minus h squared. Another way to think about this is this. Notice that this statement is a true statement here, okay? Furthermore, also note that h over here was completely arbitrary. This height was anything we could have chosen. We could have been up here, could have been down here, whatever. It was completely arbitrary. Now, note that in this situation, the cross-sectional, so in this way, you can think that the cross-sectional areas of these 2 circles, when added together, gives you the cross-sectional area here. And note that this is true for every h up. Now, wait a minute. This sounds really familiar here, right? The fact that you have the cross-sectional areas being the same all the way up, the same cross-sectional area all the way up. That should remind you of Cavalieri's principle, which we looked at a couple lessons ago. Now, that'd be great, except for the fact that Cavalieri was known for being alive in the about 15 to 2,000 years after Archimedes here. So Archimedes, in essence, also presaged this idea of Cavalieri's principle. So he figured, wait a minute, if this is always true, if this is true for the area of the cross-sections, it should be true for the volumes as well. So therefore, we can say something about the volumes here. So the volume here, now we know the volume of this solid here is just 1/3 the area of the base times the height. So it's 1/3 pi r squared times the height, which is r. And so plus whatever this is just pi times the radius squared times the height, which is r. Oops, that's an r. Therefore, we have 1/3 pi r cubed plus blah equals pi r cubed. So therefore, we can determine that the volume of the hemisphere is just this minus this. Now this is a full pi r cubed, and that's a third pi r cubed, so we subtract those two, and we end up with 2/3 pi r cubed. But wait a minute, this is half a sphere. We want the full sphere, so that means the sphere, the volume is just this times 2. And we end up with that. The sphere is just 4/3 pi r cubed. Now, the nice part about this also, ladies and gentlemen, is that if we take a look at this, we had this. This was, in this case here, we can write this as 2/3 pi r cubed. We note that there's a 1/3 here, and that's a full here, which means that we actually have a very nice relationship here. This, we can say that's 1 to 2 to 3.